Hey guys, welcome to a new video on this computer vision tutorial. In this video here, we're going to do live camera trajectory estimation. So in the previous videos, we've been using the kitty data set to estimate the camera driving around in the environment. But in this video here, we're going to combine that code with a camera or like a live webcam that we can attach to our computer. So we can just plug in a USB camera and then we can actually track that camera trajectory live in OpenCV here. But first of all, remember to hit the subscribe button and notification under the video here. Only 10% of you guys watch these videos here are actually subscribing to the channel. It's just a single click and it really helps me and the YouTube channel out in a massive way. You can also become a member of the channel if you want to support the channel with a small monthly fee. Everything will go to create more and better quality content here on the channel. Also, if you're a member of the channel, I can help you out in your own projects. If you have some problems, I can help you out, give you some guidance and so on if you're a member of the channel. So thank you guys. So for this video here, we're just going to jump straight into the code. I'm going to show you the code, how we can actually estimate the camera pose by looking at features and track those features around in the image frame from frame to frame. But first of all here, we need to import these different kind of modules that we need. So we need like our operating system, we need NumPy to do multiplication operations with matrices and so on. Then we also need OpenCV. So we're going to use OpenCV with Python in this tutorial here, as we already did in the kitty tutorial where we did visual odometry. So this is kind of visual odometry, but just with a live webcam that we have on a USB. So just have a USB webcam, then we're going to track it around in the environment live instead of just doing it for a dataset like the kitty dataset as we've been doing in the other videos. But here we're importing the different kind of modules. We also need the time module. We need matplotlib, so at the end of the program we can actually display the whole trajectory that we have moved our camera. We also need something called PyTransform 3D, so we can actually plot the different kind of camera rotations or the transformations of all the cameras that we have in our actual trajectory. And then down here we just have cycle here, so we can actually cycle between some RGB values, so we can display the camera poses as different colors when we're going to plot it with PyTransform 3D. All of these different kind of modules can be pip installed. You can just go into your Anaconda terminal or your standard command prompt. You can just pip install all these different kind of modules and you'll be good to go. All the code here from this video will be down in the description here. I have a link to my GitHub. You can just go in there, take the code, clone the repository, just run the code here on your own machine, and you can do live post estimation of your camera or camera estimation, and you can then track your trajectory while you're moving your camera. So this is actually a really nice project here that we're going to do. It can be used for a lot of different kind of things. Let's say you have a robot where you want to localize where is it in the environment. We just have a robot driving around the environment. Then we need to take care of we need to localize our robot, where has it driven and so on. It can be used for a lot of different kind of applications. We can also attach it to our car. We can maybe go out in a car, drive around the environment and see if we're actually able to tell or estimate where are we driving in the environment and then match that with the GPS data. But here, first of all, we're just going to jump in. We're going to create our class, which will be called camera poses. So this is the class that estimates all the camera poses, and then we're just going to display that with OpenCV. So here, first of all, we're going to have this initialization function or this constructor for our camera pose class. We just take in the data directory. We're not going to use that. That was for the kitty dataset. So again, if you want to know more details about these lines of code, if I skip something or something like that, make sure to check the other videos out I have about visual odometry. In this video here, we're going to focus on a monocular camera. So we're only going to use a single camera and then estimate the live trajectory of that camera. Where when we did the visual odometry, we both did it with a monocular camera, but also with a stereo vision camera. In this example here, we're not going to skip any frames, and then we're going to initialize our camera poses here with our intrinsic camera parameters. So you can estimate, you can calibrate your cameras before you actually run this code to get a more and better, better and more robust results when we're actually going to do this live estimation of our trajectory. Again, I have calibration files here on my channel as well. I have good videos about that as well. You basically just need to generate your data set. I have a file where you can just capture images of a checkerboard, and then you can just capture those images, pass them through a Python script that I have on my GitHub, and also have videos about the whole process here on the channel. So make sure to check that out so you can calibrate your camera first of all, so we get a more precise and more accurate estimate of your trajectory of your camera. Again, everything on my GitHub, you just run the code and you'll be good to go, just as in this video here. So here, first of all, we're initializing our K matrix here with our camera's intrinsic parameters, and we also initialize our extrinsic parameters. So we have no rotation and no translation for our extrinsic parameters. So basically we just start a camera at the 0th index. So we just start it at one position, and then we're going to estimate how is it actually like moving when we run a program here with respect to the camera, like the starting reference frame that we chose. So here we can have our projection matrix, which is basically just our intrinsic parameters multiplied with our extrinsic parameters. And this video here, we're going to use the orb feature detector. So we're just going to create this orb create instance, or like this method here, or like this class here from OpenCV. So we can basically just initialize it here with 3000, which is the number of features, or like the maximum number of features that we want to detect in each frame. It could be lower, but it could also like be around like 1000 features. It really depends on the environment and how many features is it able to actually like detect in that environment. So here we just have some index matches. So we set up a flange based matcher, so we can actually like match the descriptors and like the key points that we track in our image, or like we detect in our image. So we can actually like get the best key points, and then we can track those key points over a number of frames, and then we can actually like tell what are the good features that we can actually like base our post estimation of for our camera. So here we're just going to have an empty list with all the world points, so we can actually like also get all the world points. So we can actually like do simultaneously localization and mapping. So you guys might have heard like of Visual SLAM. So we can both create a map of an environment by just storing all the world 3D points. So we can actually like have a camera where we're moving around an object, and then we can capture that object from different kind of angles. If we combine all the 3D points from all the camera poses, and we also have all the camera poses, then we can actually like just multiply for each of the individual poses that we're estimating our camera. We can multiply our 3D points with that. So we combine them into the same reference frame, and then we can actually like do reconstruction with a monocular camera moving around in the environment. But that's for another video. Again, make sure to subscribe to this channel here, and also hit the bell notification so you get notification when I upload new videos, like all these cool videos and projects here about visual odometry, 3D reconstruction, and how we can use vision for real world applications. We also have a current pose here equals to none. First of all, we don't need to load in any images. In this video here, we're just going to open up the webcam. Then we just have a method here to transform like rotation matrix and also translation vector into a transformation matrix. So we won't use that either. This is just how we can combine it into our single transformation matrix that we can then store and display later on. We can also get the world 3D points here, which basically just returns the list that we just initialized. And then we can also get the matches here. So we pass in the first image and we pass in the second image. And then we're basically just going to call our op detect and compute. So here we're finding the key points and our descriptors in our images with orb. When we're going to run it here, we can actually see if we can actually go down here and show the matches that we're displaying, or like that we're matching in the environment. So if you just comment in these 3 lines of code, you will also it will also visualize what are the matches, what are the key points that we actually have in our image. But in this video here, we're just going to take the matches, we just get the key points, we take the matches, and then we just do a pose estimate. And then what we're going to visualize is just the camera moving around with the estimated trajectory live. So here we have a key point, we have the descriptors now from this detect and compute from orb. Then we can check if we actually found some matches, or if we have more than 6 matches in our first image and in our second image. Then we're just going to match those descriptors for our key points up here at the top. And then we like to have all the matches stored in this variable. Then we can run through something called loss ratio, where we basically just look at the distance from all the matches that we have from our KNN matcher. So we're going to use the K nearest neighbor matcher. So basically here we just have a for loop running through all the matches, checking if the distance is lower than another distance for another match. And if it's lower than that threshold, then we actually say that this is a good match that it has found between the key points, because the distance is not that far from each other. Then we just have a vector here, or like a list, where we just append all the good matches that we have. So basically these good matches here are the ones that we're going to do our camera pose estimate with. Then we can also get the image matches, we can draw the image matches, and then we can also visualize them if you want to do that. Down here at the bottom, we just get the Q1s and Q2s, which is basically just the image points from our good matches. We basically just run through all our key points in our good matches. So we run through M in good matches, and then we just take the point of our Q index and our train index, and then we just store it in our Q1 and Q2 here. So all of these will just be image points, or like 2D points for all the key points that we have detected in the image, and filtered by the loss ratio up here, which is inside our good matches. Then we're just going to return Q1 and Q2 from this function. So now we're going to look at the get pose function here. It takes in the Q1 and Q2 as arguments, which is just the outputs from our previous function up here, which was called get matches. So we call get matches on the first image and the second image from our webcam, and then we actually just return the 2D coordinates or like the 2D points of our key points that were detected, and those points will be the input to our get pose function here. So the first one here is just find the essential matrix from OpenCV. Again, I have another video about visual odometry where we go over the theory. I have a couple of slides where we go over what's the essential matrix, what it can be used for. And here we're just using the OpenCV function to find the essential matrix from our Q1 points and our Q2 points. But we also need to pass in the intrinsic parameters of our camera. That will return the mask and also the essential matrix here that we can then use later on to do decomposition of. So the idea behind decomposition is actually just to find the rotation and translation of our camera from one frame to the other frame of these different kind of key points that we have tracked. So definitely check that video out. I have all the theory about like why do we need to decompose the essential matrix, how do we get the rotation and translation out from the essential matrix, because we will actually get 4 rotation and translations, but we actually only need the correct one, which will be a single rotation and translation. But how to find that is in the other video about visual odometry with a monocular camera. So definitely go check that out if you want to know the details of like how we can find the rotation and translation of our camera based on our essential matrix. So basically this function here, we just pass in our essential matrix and our Q1 and Q2 points, which is the key points that we have detected. So if you just go down here and take a look at the decomposition of our essential matrix, we basically just form a transformation here. So we just use OpenCV to decompose our essential matrix. Then we will get a rotation or like 2 rotation matrices, and then we'll get a translation. So basically we have now 4 transformations because we have R1 with the positive translation, and then we have R1 with the negative translation, and the same thing for our R2. So we then have 4 different kind of transformations down here. We just create a list with all these transformations. Then we can actually concatenate here. So we can homogenize our K values with the intrinsic parameters. So we can then do linear algebra. Then we can also get all our projections here. So we basically just predict our transformation here with our camera. So we just multiply our intrinsic parameters with our transformation. So we're going to do that for all the 4 transformations that we have. Then down here, we can just run through, we can zip our projections and our transformations. Then we're going to triangulate our points so we can actually get the 3D world points of our transformations and also our projections. So the idea behind here is that we're just going to sum all the 3D points that we actually like project or like triangulate from our Q1 and Q2 tracked points in the image, or like detected key points in our image. And then we're basically just going to append that with the total sum, and then we're going to use relative scale, which we'll also talk about in the visual odometry for monocular camera video, where relative scale is basically just what we need because we only have relative information from our camera. We don't have a stereo camera where we can get like accurate 3D information. So we have the relative scale problem that we're going to solve in this way here. Then we're just going to add to our positive list, or like a positive lift, the total sum plus the relative scale, because if we don't use the relative scale, it doesn't know it, like if we're in a really large environment or like if we're just in some kind of like toy environment. So we need to take into this relative scale into account. Then we actually just run through all the positives here that we have. We take the maximum value because we just want to find the transformation that yields the most positive 3D points in front of our camera, and then we can actually like take that transformation, which will be the correct transformation from our decomposition of our essential matrix. So this is basically all it does. We can just throw back this function here so it doesn't mess everything up, and it just gives a better overview. So here we get the pose, we decompose our essential matrix into the correct rotation and translation, and then we can basically just like this will be the final transformation of our camera. So we use the essential matrix to estimate the rotation or like the transformation of our camera. Then we're just going to form a transformation from a rotation and also from our translation. So we basically here we have a transformation matrix which has 3 rows and 4 columns, where first of all we have the rotation, and then we have the translation vector in the last column of our transformation matrix. Then when we have the pose, we can basically just return that pose, and then we can use that to estimate the trajectory and how our camera is moving from frame to frame. So now we actually like have everything. So we're able to run our code here. First of all, we need to import our intrinsic parameters. I have just stored them in as a NumPy file. So here we're just going to load in the intrinsic parameters here from this NumPy file, and then we will store it in this intrinsic variable that we didn't need to initialize our camera pose object up with here, and then we just call that VO for Visual Odometry. We can just skip those here, skip frames. We don't need to take that into account when we're using a live webcam. Now we're just going to have a couple of lists here, so we can act like append our ground truth path and also our estimated path, our camera pose list, and so on. We can also have a start pose, a start translation, a start rotation, and a start pose, which will just be a concatenation of our start rotation and translation. So this is basically just setting up different kind of things and making some lists that we can store our results and variables on, so we can then display them later on with NumPy or like with matplotlib. Then we're going to open up our webcam. We just have cap equal to cv2.video capture, take the 0th index, and then we just check here if we're able to open up the camera. If we're not able to open up our webcam, we're just printing out an error opening the video stream. Then first of all, we need to set process frame equal to false because we're going to use consecutive frames. So we need the first frame and we need the second frame. So first of all, we run our code through and then we just store the old frame. So we actually like skip one frame and then we wait for the next one before we can actually like process it because we need to detect the key points from the first image to the second image. Then we're going to have a variable for old frame and our new frame, and we can also have a frame counter here so we know like how many frames have we actually like processed. We set our current pose equal to the start pose that we just initialized up here at the top. Then we can have a while loop, which is just the main function here that we're going to run. So we have a while loop running as well as the webcam is open. Then we're just going to read in a new frame. We store that in our new frame variable. We just increase our web counter by 1. Then we start a timer so we can actually like time how long it takes to run this algorithm here through, so we can then estimate the frames per seconds that we get from our system here by estimating the pose and doing live trajectory estimation of our camera. So here, if we're going to process frame and the return value here is true, so we're actually able to read a frame from our webcam, then we're just going to call the functions that we just went through. We are going to call vo.getMatches. We pass in the old frame and the new frame. So basically here, it just detects the key points, it matches the descriptors and key points in the image, it filters the key points with loss ratio, and then we basically just return those points. And then if we're actually able to detect some points, and if we're able to detect more than 20 points, we will then estimate the pose based on all those Q1s and Q2s that we found up here in the matches. And then Visual Odometry.getPose, it returns the transformation that we have estimated by actually like finding the essential matrix based on these points here, and also decomposing it to find the correct transformation of our camera. Then our current pose will be equal to our current pose multiplied with the new transformation. So this is actually just, we start as one position with our camera, then we move our camera here, we estimate the transformation from this position to this position, and then we just multiply it so we get our camera over here. So this will be a new current position. Then we can move our camera over here a bit more. We'll estimate the transformation again, multiply with the current pose. So we then go from here to here. And then we just keep doing that for all the frames that we're actually like loading in from our webcam. Then we have an homogenized array here. We have a camera pose where we're just concatenating these values. And then we're just going to append our camera pose to our camera pose list, and also our estimated path. We're going to take the X value and the Y value, so we can actually like display it in a 2D world when we're going to do it with matplotlib. So when matplotlib, we're just going to display the 2D movement or like the 2D trajectory of our camera. We can also take the first element here of the list and we'll get the 3D information as well. So here we can see the estimated camera pose X and Y. We just set that equal to the current pose of these indexes. It is basically just the same as what we append to our estimated path list up here. Else, if we're going to process our frame and we can't read in a new frame here, we'll just break off the while loop and we'll terminate the program. So that is because our camera can read in more frames. So we can also actually use this on videos here, and it will just break out here if there's no more frames to load in from that video. So if you're going to use a video instead of a camera live webcam, you can basically just pass in the path to the video up here instead of the 0th index for our camera. Also, if you have more cameras attached to your computer, like USBs and so on, you should maybe like try some other different kind of indexes here. I just have my camera on the 0th index in this video here. So then down here, we have now our old frame. So our old frame will now be equal to the new frame. And then we set process frame equal to true. So the first time we run through this while loop here, we will not do all of this processing here because our process frame is equal to false. And then when we actually have an old frame, we set process frames equal to true because then we both have an old frame and a new frame. When we read in a new frame from a webcam up here, then we can detect features in the old frame and the new frame, and then we can estimate the transformation between those two. Then we're going to end our counter because now we have done all the processing, and we can then time and see how many frames per second do we get. Down here, we're just going to put the text of the number of frames per second, and then we're basically just going to display our transformation matrix. So here we will have all the rotational part, and down here we will have the translational part. So we can actually see how is the camera rotating and translating in the environment when we're going to run our code live on our image show as well. So then we're just going to call an image show here with the new frame and the image. And this is also where all the information of the rotation and the translation will be displayed on. So we can track around, we can see what the camera actually sees in the image, and then we can display what is it estimating at the same time. So this is actually really nice. Down here, we're just going to have an if statement checking if we hit Q on our keyboard. If we do that, we will just go inside this if statement and we will break out of the while loop. It will terminate our program. It will release the webcam down here at the bottom. So the last code here before we're going to actually run this script is just for like plotting. So down here we just have like a number of frames, the camera poses. We're just going to set up some camera indexes, and then we're just basically just going to plot the 2D trajectory of our camera. So we're doing it live, and then we're just storing all the information while we're doing it live. And then when we terminate a program, we will just use matplotlib to actually like display the whole path from when we started the program to when we terminated the program. And then we'll do it with matplotlib down here at the bottom. So let's now run the program here and see how it actually works. So first of all, we're just going to run the program. Here we have my webcam attached to the USB. So here we can see the starting position. We can see the rotational part here. That doesn't really like make that much sense, but we can see like if there's no rotation, we'll just have like the identity matrix. So we can see that here there is actually like a rotation from the starting position. Over here to the right, we can see the translation from the starting position. So we can see that the C value here is a bit further away from the starting position. But if I go closer to the computer here, like the computer screen, we can see that we get a more negative value or like a higher negative value for the estimation of our depth. So we have actually moved the camera in this direction here. If we move it further back, as you can see, we can see that the value here increases. So here we can see that we're now like 10 units or like 8 units away from our starting position of our camera. We can also see if I move it in the other direction here, we can see that the X value up here at the top changes. So now we have a negative value. Here we have around the starting position, which is actually like the correct starting position. So even if we go back to the starting position, it can also estimate that. And now we're just actually, we just have a camera looking towards my monitor here. It doesn't really detect that many key points. If we have an environment with more key points, we will actually get better results. But if we're moving further away, we can just see that the C value increases. We can also rotate the camera here, and you can see that it actually like rotates in the rotation matrix as well. We get around 10, 14, 15 frames per second. It really depends on the number of key points that we're detecting. If we're not detecting any key points, if we just take it down here, then we can see that we get around like 80, 90% FPS because we're not doing any processing at all. But if you take it up here, it takes some key points, and then it just takes up a lot of computational time. You might actually get a bit lower frames per second if you have a more complex environment. I can try to run the code and maybe move around in the environment behind me and see if it lowers the FPS, and also if we're still able to detect the live trajectory of our camera. So here we're just going to terminate our program so we can actually see all the different kind of like camera angles here that we had. So we can see that we had a starting position around 0.0, and then we have moved the camera a bit up, and we have also moved it to the sides, and then we also moved it back here at the back of the, like further away from the monitor here, as you also saw here in the video. So these are actually like the correct poses or like the correct transformations of our cameras. So we use PyTransform to visualize this one here in 3D. But we also did this with matplotlib. So this is the 2D trajectory of our camera. So here we're just displaying all the transformation that were estimated. You should probably filter those out, take some moving averages and so on off the transformations. But here we can see that the camera, we just kind of moved it around like this. And if we're just holding it still, we might get some like a lot of fluctuations here in the trajectory. But overall, this is actually like a really nice live camera trajectory estimator that can be used for a lot of different kind of applications. So here we're just going to run the code again, and I'll just like point the camera out in the room so we can actually like get some more features that we can detect. Here we can see we get around like 15 frames per second. I'm just going to move it around, and then we can look at the trajectory up at the top of our image that we're estimating. So we can see that sometimes it actually loses track. It doesn't estimate a pose because it doesn't have enough key points in the image. So if it goes too far, it is not able to detect any key points. And if the camera doesn't focus or something like that, then we're not able to detect the key points enough, and then we can't estimate the pose. But the next time we're able to detect the key point, then we will actually like estimate the correct path. It might fluctuate, like the error might get bigger because we took like a bigger step, but we're still able to estimate the transformation of our camera. You could just say hi to my dog in the background there. Thank you for your demonstration. But here we can see that it just estimates the trajectory like really nicely. We can see here we're around like, we can see that it is actually like the correct X position and also the Z position. So we can see that when we move forward towards my dog here on the couch, it actually like decreased the Z value because we're moving further away from the starting position that we defined. And also we actually like when we move further away again, when we move back to the starting position, it actually like increased the Z value and also the rotation. It seems to be pretty good. If we just point it over here in the room again, and then we just rotate our camera, we're able to detect, and we can actually like see the rotation changes a lot here in the rotation matrix. So this is a really nice live camera pose estimation of our camera trajectory. It can be used for a lot of different kind of applications as we have already been over. So we've been through all of this here. If you want to know more details, definitely check out our Visual Odometry videos here on the channel. We go way more into details, but this is just to show you guys what it can be used for. Again, you can just go into my GitHub, take the code, download it, run it on your own computer. Maybe you should calibrate your own camera so you get a bit more accuracy on your side with your own camera. But then you should actually just be able to run the Python script and you will get the exact same results as I have and I just showed you here in the video. So thank you guys for watching this video here, and hit the subscribe button and bell notification under the video here. It just really helps me and the YouTube channel out in a massive way. Also like this video here if you like the content and you want more in the future. We're probably going to make some other videos where we're actually like going out in a car, driving around in the environment, try to track the path that we're driving in our car, and maybe we can match that with some GPS information and see if we're actually like able to detect the camera or like the car position in the environment while driving around, as in the case with the kitty data set. But if you're interested in my computer vision tutorial where we talk about like camera calibration as we've used in this video, visual odometry, like standard like basic image operations and so on, I'll link to the computer vision tutorial up here, or else I'll see you next video guys. Bye for now.